Math 10150 Lesson 8, and in this video we're going to do polynomial inequalities. We already did linear inequalities and polynomial equations. Now we're going to combine the two concepts and do polynomial inequalities. So first we need to recall some facts. So solutions to linear inequalities were intervals, but solutions to polynomial inequalities will be intervals or unions of intervals. So an example of a union of intervals looks like this: 1, 2, including 2, not including 1, union 5 to infinity. So this is a union of intervals. If we wanted to graph it, it would look like this. We would include 1, we would include not 1, but we would include 2, and then we would include everything to the right of 5. So this is a union of intervals. And that's how our solutions are going to look like. Another thing to recall is just the properties of real numbers. So properties of real numbers. Just like we solved polynomial equations by factoring, we're going to also solve polynomial inequalities by factoring as well. And then we're going to look at the signs. So recall the facts of real numbers, how signs work. If you are multiplying a positive number times a positive number, you're also going to get a positive number. If you're multiplying a positive number times a negative number, you are going to get a negative number. If you're multiplying a negative number times a negative number, you are going to get a positive number. So that's important to remember when we are looking at factors of polynomials. Another fact about signs is what happens to signs when we take them to powers. So if we have something, let's call it u, if we have something to a power, then it's always going to be positive if n is even. So things to even powers are positive. For example, u squared is something squared is always positive. Something to the power of 4 is always positive. If you have odd powers, then u to the something is positive if it itself is positive and m is an odd number. So if you take a positive number to an odd power, it's going to remain a positive number. And if you take a positive number, if you take a negative number to an odd power, it's going to remain negative. So if you take negative 3 to any odd power, it's going to be negative. If you take negative 3 to any even power, it's going to be positive. So those are just properties of real numbers to remember. So how do polynomial equations look like? Polynomial inequalities look like polynomial equations. Just instead of an equal sign, we have a less than or equal to sign. We're first going to start with a baby polynomial equation, which is in fact a linear equation. These are things that we are familiar with. So if we are asked to solve something like this and graph the solution, well, x minus 3 is greater than 0. When is it possible for x minus 3 to change sign? Well, it can only change sign at 3. So If it is on the right side of 3, it's going to be positive. If it's on the left side of 3, it's going to be negative. If you plug in a number that's higher than 3, then x minus 3 is going to be positive. If you plug in a number less than 3, it's going to be negative. And so the solution to this simple linear inequality is just 3 written in interval notation is 3 to infinity. Now we're going to look at a polynomial equation, and I mean linear equations are the simplest example of polynomial equations. So let's look at example 2. Very similar, except now we have x plus 1 and x minus 3, and we ask what is the solution to this inequality. Well, now we have a product of two things, and like we were called products of positive and negative numbers is positive, and products of a positive and a negative number is going to be negative. And that's what's going to determine when this inequality is true or false. So there's only 2 points on the real line where this polynomial x plus 1 times x minus 3 can change sign. And one of these points is x equals negative 1, and another point is x equals 3. Sometimes these are called partition points. But really, I mean, you can just think of them any potential points where our inequality can change sign. And we plot them on the real line. And then we look at the signs of our factors. And then we decide when is it positive. So if we plug in something that's greater than 3, we can take a test point, or we can just in general think, well, if something is greater than 3, then x plus 1 is definitely going to be positive, and x minus 3 is also definitely going to be positive. And so this means that this is going to be everything that's greater than 3 is going to be positive. Now let's look at what happens when we go pick a number between 1 and 3. We can pick a test point, let's say 2. If we plug in 2, we're going to get 2 plus 1, that's positive, times 2 minus 3, that's negative 1, that's negative. We're going to get a positive number times a negative number. Because if we plug in something less than 3, it doesn't matter that it's greater than 1. If we plug in anything that's less than 3 into x minus 3, we're going to get a negative number. And so the result that on the interval from 1 to 3, whatever number we plug in on that interval, we're always going to get a negative number in the expression x plus 1 times x minus 3. Then we look at the last piece. Well, if I plug in anything that's less than negative 1, if I plug in anything that's less than negative 1, I'm going to get negative numbers. So if I plug in, let's say, negative 2 minus 3 is a negative number. Negative 2 plus 1 is a negative number. So then we're going to have 2 product of 2 negative numbers. But if you multiply 2 negative numbers together, you're going to get, again, a positive number. And then once we analyze the real line like this, we're ready to write down our solution. Our solution is negative infinity to negative 1, union 3 to infinity. This is all the points on the real line that satisfy this polynomial inequality. Notice we would do the exact same procedure if the inequality was x plus 1 times x minus 3 less than 0. We would just simply choose the interval negative 1, 3 as our solution. If this is a strict inequality, so we do not include the endpoints in our final solution. So analyzing the signs of the numbers in each subinterval from 3 to infinity, from negative 1 to 3, from negative infinity to negative 1, we can get the sign of the result of this product of this polynomial in each interval. So let's look at another example. Here we have the polynomial 2x squared less than or equal to 3 minus x. This is our inequality. And just like polynomial equations, if our polynomial is not factored, we need to factor it and set one side to 0 before we can solve it. Whenever you're manipulating polynomial inequalities, be careful to never divide or multiply by a constant. You can subtract and add. I mean, you can never multiply and divide by variables because those variables may be positive or negative, and you don't know whether your inequality flips or not. You can always subtract and add variables. So that's what we're going to do here. This is 2x squared plus x minus 3 less than or equal to 0. And we factor it just as if we were solving a polynomial equation. And factored, this is 2x plus 3, and this is x minus 1. Now the potential points at which the sign of this polynomial can change is given to us by the factors. The 2x plus 3 is going to change at negative 3/2, or may change, and the x minus 1 may change at x equals 1. So when we look at our real line, there are two potential points where the sign change can happen. And we look at the first region, anything that's greater than 1. And if anything is greater than 1, then both factors are positive. So we have a positive number times a positive number, giving us a positive number on this interval. The second piece, from negative 3/2 to 1, well, x minus 1 is negative there because anything less than 1 is negative. The other piece is still positive. So we have a positive times a negative, which gives us a negative. Anything that's less than negative 3/2, we're going to have a product of two negative numbers. If you plug in, let's say negative 2, then negative 2 minus 1 is negative, and 2 times negative 2 plus 3 is also negative. However, a negative times a negative is going to be a positive. And now we look what our inequality is. We need to be less than or equal to 0. So then we look, where is this polynomial negative? And it is negative from negative 3/2 to 1. And we use brackets because this is less than or equal to inequality. And this is our final solution. Next, we have the following inequality: x minus 1 squared greater or equal to than 4. Now, this looks kind of factored. However, there's no 0 on one side. So we need to expand and get the 0 on the other side because we need an inequality that is not just factored, but factored and less than or equal to or greater or equal to than 0. So what we do is we FOIL this out, x squared minus 2x plus 1, which is greater or equal to than 4. Subtract 4 from both sides, and we get x squared minus 2x minus 3 greater or equal to than 0. Just as before, we factor into x plus 1 and x minus 3 greater or equal to than 0. And the potential points, the partition points where this can change sign is negative 3 and 1. And we again draw a number line to help us visualize. So anything that's greater than 3, we're going to have a positive number times a positive number, giving us a positive number. Anything that is between -1 and 3, x plus 1 is still going to be positive. Whereas the factor x minus 3 is already negative because we're less than 3. And a positive times a negative will give us a negative. If we're below -1, then both factors are negative, thus giving us a positive number. Now this inequality asks us to solve when are these factors greater or equal to 0. So the solution is going to be from -infinity to -1, including -1, union 3 to infinity. Let's look at the next example. We have x to the 4th greater than 7x squared minus 6. And again, at first this looks kind of intimidating because there's a power 4 to it. But really this is quadratic in form. We can recognize that. And again, we need to factor it and bring everything over to one side. We can factor this using substitution. Where y equals x squared, just like we solved those polynomial equations. So now we have y squared minus 7y minus 6 greater than 0. This is a quadratic which we can factor. This is a quadratic which we can factor into x minus 1 and into y minus 1 and y minus 6 greater than 0. But our problem was not in y, so we need to now switch everything back to x's. This is in fact x squared minus 1 and x squared minus 6 greater than 0. And these are both differences of squares, so this gives us x plus 1, x minus 1, x plus radical 6, and x minus radical 6 greater or equal to 0. We have 4 possible points where this inequality can change sign. The first one is at x equals -1. The second one is at x equals 1. The third one is at x equals negative radical 6. And the fourth one is when x equals radical 6. Radical 6 somewhere between 2 and 3. So we can plot that on a real line. Radical 6, 1, -1, and negative radical 6. So these are the only places where this polynomial can change sign, and we're interested when is the product of these 4 things positive. So now we have a product of 4 things, and let's look at that. So if something is greater than radical 6, all four factors must be positive. So if we have positive times positive times positive times positive, our result is certainly positive. Now let's see what happens between 1 and radical 6. Again, we can choose a test point like 2, or we can analyze which of these factors is going to become negative. And the last factor, x minus radical 6, is the only one that's going to become radical if we are less than radical 6. So we have 3 positive numbers times a negative number, which gives us a negative number. Now we can look what happens between negative 1 and 1. The next factor that starts being negative is the second one. So now we have positive times negative times positive times negative. This gives us something positive because there's an even number of negatives. And then let's look at what happens between negative radical 6 and negative 1. The next one to go negative is the first term, the x plus 1 term. X plus 1 here is already negative. X minus 1 is still negative because we're less than 1. X plus radical 6 is still positive here because we're greater than negative radical 6. And the last term, x minus radical 6, is still negative. And so we have 3 negatives and 1 positive, giving us a negative. And finally, the last piece, once we're below negative radical 6, all 4 factors turn negative, giving us a positive number in this interval. And now we need to find all of the intervals in which this is positive. And so our final solution is negative infinity to negative radical 6, union negative 1 to 1, union radical 6 to infinity. And this is our final solution. Again, if you prefer, you can take 1 test point from every single interval. For our final example, we're going to take a look at how can we take advantage of powers of positive and negative numbers, and we'll look more at this when we do rational inequalities later in the course. So let's say we have this example, x squared plus 4 times x minus 3 squared times x plus 4 cubed times x, when is that less than or equal to 0? So there's several things here, and we can look at each factor. So this piece is always positive because x squared is always positive. X squared plus a number is also always positive. This piece, because of this 2 here, is also always positive. That's why at x equals 3 is not going to be one of the places where something can change sign. This next piece, x plus 4 cubed, is going to be positive or negative if x plus 4 is positive or negative. So this next piece, x plus 4 cubed, is positive if x plus 4 is positive, and x plus 4 cubed is negative if x plus 4 is negative. So the potential points that can contribute to a changing of sign is x equals negative 4 and x equals 0. And we're going to look at the real line. We can ignore those 2 factors and just look at 0 and negative 4. And let's look how our signs are. So we're just looking at x plus 4 cubed times x. So if we're greater than 0, then I'll put the first 2 terms here just for visual appeal. The first 2 terms, x squared plus 4 and x minus 3, are always positive. If we're greater than 0, then x plus 4 cubed is positive, and x is also positive because we're greater than 0. If we're between and so anything from 0 to infinity is positive. Now we're going to look between -4 and 0. The first two terms remain positive as always. X plus 4 is still positive. If you take any test point, let's say x equals -2, -2 plus 4 is a positive number cubed is still positive. So this is going to be positive. However, we're less than 0, and so x is going to be negative. And so everything here from -4 to 0 is negative. Below -4, the first two terms are positive as always. However, x plus 4 cubed is now negative, and x is still negative, and we have positive number here as a result. And now the inequality wants us to know when is this less than or equal to 0. So the final solution is -4 to 0, and we use brackets because this is less than or equal to. So whenever you have a factored polynomial and you're solving an inequality, always look for which factors are always positive, and then you can essentially ignore them when you think about the signs.